September 19th, 1944. The fog-shrouded plains outside Aracourt, France. Oberstleutnant Werner von Seegroth pressed binoculars against his weathered face, scanning for the American positions that had evaded his reconnaissance patrols since dawn. Commanding the 113th Panzer Brigade's lead assault element, he possessed what German doctrine considered overwhelming advantages: 42 Panther tanks, each mounting the 75mm KBK-42 guns, capable of penetrating Allied armour at ranges exceeding 1,500 metres. Sloped frontal armour, 80mm thick, rendered these machines nearly impervious to standard American tank guns. A proven top speed of 46 km per hour that German engineering had refined through 3 years of Eastern Front combat. His crews represented the latest generation of Panzer doctrine, trained on vehicles that embodied everything German military philosophy valued: precision manufacturing, sophisticated mechanical systems, overwhelming firepower concentrated in platforms designed to dominate any battlefield engagement through technical superiority. The Panthers, advancing through this French countryside, cost 117,000 Reichsmarks each, machines that required 25% more labour hours than earlier Panzer IVs, but delivered capabilities that justified every additional minute of Krupp's precision metalworking. Von Seegroth's confidence stemmed from verified battlefield mathematics. American tank destroyers captured during previous engagements had proven disappointingly inadequate. The M10 Wolverine, essentially a 3-inch gun mounted on Sherman chassis, lacked both the armour and firepower to challenge Panther supremacy. Intelligence briefings described American tank destroyer doctrine as fundamentally flawed, emphasizing mobility, without understanding that speed meant nothing without survivability and sufficient penetration to defeat modern German armour. The morning's objective required straightforward execution: advance through the fog, locate American defensive positions around Rechicourt-la-Petite, engage with main guns from maximum effective range while American return fire bounced harmlessly off Panther glacis plates. Repeat this proven formula until the remnants of Patton's 4th Armoured Division withdrew across the Merthyr River, abandoning their exposed bridgehead. What von Seegroth couldn't know as his Panthers rumbled forward through visibility measuring less than 30 metres, was that American tankers waiting in concealed positions ahead had never seen anything like the machine they were operating. The M18 Hellcat represented a radical departure from conventional tank destroyer philosophy, weighing 17 tons against the Panther's 45, mounting armour protection measuring just 12.7mm at its thickest point, less than half an inch of steel separating crews from incoming fire, but capable of achieving 55 miles per hour on level roads through a power-to-weight ratio that made German engineering specifications appear conservative. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The vehicle, sitting in Lieutenant Edwin Leiper's position outside Rechicourt-la-Petite, shouldn't have existed according to German technical assumptions about armoured warfare. American designers had violated every principle that guided Panzer development, creating something that Werner von Seegroth's tactical training had never prepared him to confront. The collision between these competing philosophies, between German engineering perfection and American industrial pragmatism, would unfold across the next 72 hours in ways that challenged fundamental assumptions about what made effective armoured combat vehicles. The genesis of the Hellcat reached back to December 1941, when American military planners studied the catastrophic defeats France had suffered 18 months earlier. German panzer divisions had demonstrated new warfare methodology that rendered static anti-tank defences obsolete through speed, concentration, and breakthrough tactics that American doctrine couldn't counter with existing equipment. General Andrew Bruce of the newly formed Tank Destroyer Command envisioned something unprecedented: specialized units equipped with vehicles faster than tanks, mounting guns powerful enough to defeat enemy armor, but deliberately sacrificing protection to achieve mobility that would enable rapid response to armored breakthroughs. The concept violated conventional tank design orthodoxy. Every major combatant nation's armored doctrine emphasized the balance between firepower, protection, and mobility as fundamental triangle requiring careful compromise. German engineers pursued perfection across all three dimensions through precision manufacturing and sophisticated mechanical systems. Soviet designers accepted crude reliability to enable mass production. British development emphasized proven automotive technology adapted for military purposes. American industrial capacity had produced the Sherman tank through compromises that prioritized mechanical dependability and ease of manufacture over optimal battlefield performance. Bruce's tank destroyer philosophy rejected this balanced approach entirely. Maximum speed, adequate firepower, minimal armor. The resulting specifications demanded unprecedented engineering solutions that Detroit's automotive industry would need to develop under impossible timeframes. Buick's engineering teams received the initial tank destroyer requirement in December 1941, a vehicle mounting 37mm gun, achieving speeds exceeding existing tank designs, using torsion bar suspension for improved cross-country mobility. These specifications evolved rapidly as battlefield intelligence from North Africa revealed German armor development had outpaced American planning assumptions. The 37mm gun proved inadequate before testing began. Requirements increased to 57mm, then 75, finally settling on 76.2mm when German Tigers and Panthers appeared on Tunisian battlefields. Each specification change forced complete design reconsideration. The T-70 GMC prototype that emerged by April 1943 represented automotive engineering pushed to revolutionary extremes. Buick's design team, led by legendary stylist Harley Earl, approached the challenge with methodology refined through decades of civilian automobile development rather than military procurement tradition. The engine selection demonstrated this automotive thinking applied to military requirements. Instead of developing purpose-built tank power plants, Buick specified the Wright Continental ER-9 75-cone radial engine already proven in Sherman tanks and various aircraft applications. 700 horsepower, driving a vehicle weighing less than 18 tons, created power-to-weight ratios approaching sports car performance. The innovative Torquematic automatic transmission, adapted from Buick's civilian vehicle program, provided smooth power delivery that enabled rapid acceleration without requiring specialized driver training for complex manual gearboxes. Weight savings came through accepting vulnerability that German engineers would have considered suicidal. Maximum armor thickness of 1 inch on the turret front. Hull protection rarely exceeding 25mm. Side armor measuring just 12.7mm, thin enough that armor-piercing 30-caliber machine gun rounds could penetrate at close range during testing. The open-topped turret left crews exposed to artillery fragments, small arms fire, and weather conditions, and that enclosed fighting compartments prevented. These compromises enabled revolutionary performance specifications that testing confirmed exceeded every requirement. Top speed of 55 miles per hour on paved surfaces. Off-road mobility, matching lighter reconnaissance vehicles. Acceleration that allowed reaching combat speed within seconds rather than the minutes required for heavier designs. The torsion bar suspension provided ride quality that enabled accurate firing while moving, an unprecedented capability that German tank commanders could only achieve through complex gyroscopic stabilization systems. The tank destroyer board received its first T-70 prototypes on December 31, 1942, beginning intensive evaluation that would span 11 months and generate 16 comprehensive reports documenting 137 modifications before production approval. The nickname Hellcat emerged during Buick's internal testing at General Motors' Milford Proving Ground, where engineers subjected prototypes to punishment that would have destroyed conventional designs. High-speed runs on banked oval tracks, specialized bumpy surfaces that tested suspension beyond any battlefield conditions, water fording to 6 feet depth, ramming through structures, wall climbing exercises. The 704th Tank Destroyer Battalion received initial production Hellcats in spring 1944 for field testing that validated or refuted engineering assumptions under actual combat conditions. These crews quickly discovered capabilities that technical specifications couldn't adequately convey. The Hellcat's acceleration enabled tactical maneuvers impossible for heavier vehicles. Sprint to flanking position. Fire. Relocate before enemy return fire arrives. This hit-and-run methodology exploited the fundamental limitation of German tank design: turret traverse speed. Panther tanks featured sophisticated turret mechanisms, providing 360-degree coverage, but rotating that turret with its 75mm gun and heavy armor plating required time measurable in seconds. Time during which a Hellcat traveling at 40 miles per hour could cover hundreds of meters, repositioning from frontal engagement where Panther armor provided immunity to flanking angle, where 80mm side armor became vulnerable to American 76mm gun penetration. German tankers trained on doctrine emphasizing frontal engagement where their superior armor and firepower dominated encounters. Panthers could absorb punishment from Sherman 75mm guns at ranges where German return fire penetrated Sherman frontal armor with devastating efficiency. This tactical advantage had proven itself across thousands of Eastern Front engagements against Soviet 34s, establishing German confidence in Panzer technical superiority as fundamental truth validated through actual combat results. The Hellcat challenged this truth through rejecting its premise. American designers hadn't attempted building better armored tank destroyers. They'd built faster ones that made armor irrelevant through avoiding hits entirely. Speed as an active defense mechanism. Mobility enabling tactical advantages that protection couldn't provide. This philosophical difference would prove decisive when Werner von Seegroth's Panthers encountered Edwin Leiper's Hellcats in fog-shrouded terrain outside Aracourt. September 19th dawned with visibility measuring less than 50 meters. The fog that tactical doctrine suggested favored the attacker through concealing approach routes and preventing defenders from exploiting long-range fire advantages. Von Seegroth's battle plan relied on this assumption, ordering his Panthers forward through conditions that would allow close approach before American positions could respond effectively. Lieutenant Leiper commanded one platoon of Company C, 700A, 4th Tank Destroyer Battalion, positioned in a slight depression that provided hull-down advantage while maintaining clear retreat routes toward Rechicourt-la-Petite. His 4 Hellcats represented American tank destroyer doctrine distilled to essential elements: adequate firepower, concentrated in platforms designed for ambush tactics rather than sustained engagement. The fog that von Seegroth considered tactical advantage actually complicated German operations more than American defensive positions, reducing Panther's long-range fire superiority to close-quarters encounters, where maneuverability would prove decisive. The first German gun muzzle materialized through the fog at a distance, measuring 30 feet from Leiper's lead vehicle. Impossibly close range that should have resulted in immediate Hellcat destruction, except the fog that concealed the German approach also prevented Panthers from acquiring proper targets. Leiper's gunner fired first, 76mm armor-piercing round striking Panther side armor, before the German crew realized American tank destroyers occupied positions directly adjacent to their advance route. The next 5 minutes demonstrated everything Werner von Seegroth's training hadn't prepared him to face. Hellcats engaged from concealed positions, fired, then relocated using speed that Panther turret traverse couldn't match. German return fire struck positions Hellcats had already vacated, while American gun crews exploited the chaos to target Panthers from angles that defeated even their sophisticated armor schemes. 5 German tanks erupted in flames before von Seegroth could organize a coherent response. Mechanical carnage inflicted by vehicles, his intelligence briefings had dismissed as inferior American improvisation. The platoon held position as more Panthers advanced through the fog, methodically destroying 10 additional German tanks while losing 2 Hellcats to concentrated return fire. Sergeant Henry Hartmann's vehicle alone accounted for 6 German tanks, most of them Panthers, through disciplined fire and movement that exploited the Hellcats' revolutionary mobility. His crew would fire, observe the strike, then sprint to new positions before German gunners could compensate, repeating this cycle with mechanical precision that German training doctrine couldn't counter. By the time tactical conditions stabilized enough for von Seegroth to withdraw his surviving Panthers, the mathematics told a devastating story. 15 German tanks destroyed in the initial engagement, American casualties, 3 Hellcats lost, Modest price for tactical victory that shouldn't have occurred according to German engineering assumptions about armor warfare. The battle continued over the next 3 days as von Seegroth received reinforcements and attempted different approaches to breaking American defensive positions. Each engagement revealed the same fundamental mismatch. Panthers designed for frontal slugging matches found themselves outmaneuvered by vehicles that refused to fight on German terms. Hellcats would appear, engage from flanks or rear angles where Panther armor couldn't protect effectively, then disappear before German tactical responses could organize. The final accounting recorded 39 German tanks destroyed against 4 Hellcats lost and 3 damaged, a kill ratio that represented complete tactical defeat for a force that had entered battle with overwhelming technical and numerical superiority. Werner von Seegroth's after-action report struggled to explain what had occurred. His Panthers had functioned exactly as designed. The guns had performed flawlessly. The armor had protected crews from frontal engagement. The mechanical systems had operated within specifications. Yet his brigade had been decimated by American tank destroyers that violated every principle of proper armored vehicle design. The contradiction demanded an explanation that German engineering doctrine couldn't provide without acknowledging uncomfortable possibilities about the relationship between technical perfection and battlefield effectiveness. The captured Hellcat that arrived at German testing facilities in October 1944 came from a different engagement. Abandoned by the American crew after mechanical failure immobilized the vehicle during withdrawal. Recovery teams transported it to Kummersdorf, proving grounds outside Berlin, where Waffenamt engineers would conduct systematic evaluation that paralleled the earlier tests that had shocked German assumptions about Sherman tank reliability. Hauptmann Friedrich Steiner received an assignment to lead the technical assessment, bringing 15 years of automotive engineering experience to bear on understanding what made the American tank destroyer so tactically effective, despite obvious design limitations. Steiner had tested captured Soviet equipment, British vehicles, and numerous German prototypes, developing a reputation for analytical thoroughness that prioritized factual assessment over ideological conclusions about Axis technical superiority. His initial inspection produced observations that seemed almost insulting to German engineering standards. The hull construction used welded rolled homogeneous armor plates without face hardening, simplified manufacturing technique that reduced costs but eliminated the surface hardness German metallurgy achieved through specialized heat treatment. The turret mechanism employed basic manual traverse without powered assistance, requiring the gunner's physical effort to rotate the fighting compartment. The suspension utilized straightforward torsion bars without the sophisticated interleaving that characterized German designs, accepting simpler maintenance over optimal cross-country performance. The engine compartment revealed automotive-grade components throughout: commercial spark plugs, standard bearing assemblies, non-military specification, gaskets and seals. Everything about the Hellcat's construction suggested civilian automotive manufacturers had adapted existing technology for military application rather than developing purpose-built combat systems through rigorous military engineering specifications. Yet when Steiner's team conducted performance testing, the results contradicted every assumption those observations had suggested. The engine started instantly in sub-freezing conditions that would require German tanks to undergo 30 minutes of preheating. The transmission shifted smoothly under load without specialized driver training. The suspension absorbed punishment that should have destroyed components designed to civilian rather than military tolerances. Most remarkably, the Hellcat achieved its advertised 55-mile-per-hour top speed during high-speed runs that Steiner's team initially believed would end in catastrophic mechanical failure. The comparison testing began in November 1944, when Steiner received authorization to conduct side-by-side evaluation against German tank destroyer designs. The Jagdpanzer IV represented Germany's answer to similar tactical requirements. Tank destroyer optimized for defensive operations, mounting a 75mm gun in low-profile casemate that provided excellent frontal protection while minimizing target signature. German engineering had produced vehicles that embodied traditional design philosophy, achieving balance between firepower and protection through accepting limited mobility and complex mechanical systems. The Jagdpanzer IV weighed 25 tons against the Hellcat's 17. Maximum road speed of 40 km per hour, compared to the American vehicle's 89. Armor protection measuring 60 mm on the superstructure front versus the Hellcat's 25 mm maximum. On paper, the comparison favored German design through superior protection and comparable firepower, concentrated in a proven platform that reflected 3 years of combat experience refinement. Steiner's testing protocol emphasized practical battlefield metrics rather than theoretical performance specifications. Time from cold start to combat-ready status, acceleration to tactical speed, sustained cross-country mobility, maintenance requirements, crew fatigue during extended operations. These measurements would reveal which design philosophy produced a more effective combat vehicle under actual wartime conditions rather than ideal testing circumstances. The cold start trials demonstrated an advantage that no amount of engineering sophistication could overcome. The Hellcat's radial engine fired reliably after sitting overnight in temperatures approaching -10 degrees Celsius. The Jagdpanzer IV required extensive preheating procedures that consumed 45 minutes and significant fuel reserves before the Maybach engine could turn over without risk of catastrophic damage. This difference meant American crews could respond to tactical emergencies within minutes, while German tankers needed nearly an hour of preparation time. Acceleration testing revealed equally dramatic disparity. The Hellcat reached 40 km per hour in 8.3 seconds from standing start. The Jagdpanzer IV required 21 seconds to achieve the same speed, a handicap that would prove fatal in combat situations requiring rapid repositioning. Steiner's crews quickly discovered the tactical implications. During simulated engagement exercises, the Hellcat could fire, relocate 400 meters, and fire again before the Jagdpanzer completed the initial repositioning maneuver. The cross-country mobility trials provided the most shocking revelations about competing design philosophies. Steiner's team established a course through mixed terrain, hard-packed roads, soft agricultural fields, moderate hills, stream crossings, and rough ground simulating shell-cratered battlefields. The Hellcat completed the course in 42 minutes, while averaging 31 km per hour. The Jagdpanzer IV required 78 minutes at average speed of 19 km per hour, a difference attributable to the American vehicle's superior power-to-weight ratio and simplified suspension design that prioritized mobility over optimal weight distribution. Most significantly, the Hellcat completed the course without mechanical failures. The Jagdpanzer IV experienced 2 track tension adjustments, 1 idler wheel bearing inspection, and required cooling system monitoring that German crews had learned through bitter experience couldn't be neglected without risking engine damage. The American design's automotive-grade components had proven more reliable under field conditions than German military specification systems engineered for theoretical perfection. Fuel consumption analysis revealed paradox that challenged German assumptions about engineering efficiency. The Hellcat consumed more fuel per kilometer than the Jagdpanzer IV, a predictable result of the powerful radial engine driving relatively light vehicles at high speeds. But tactical fuel efficiency told a different story. The American vehicle could complete reconnaissance missions, engage targets of opportunity, and return to base before the German design completed the same mission profile, despite burning fuel at a higher rate per distance traveled. Speed enabled accomplishing objectives that negated the theoretical advantage of better fuel economy. Steiner's most detailed analysis focused on maintenance requirements, an area where German engineering pride traditionally claimed superiority through precision manufacturing and sophisticated component design. The Hellcat's engine could be removed and replaced in field conditions within 4 hours, using standard tools and minimal specialized equipment. The power pack mounted a roller assembly that allowed it to slide out the rear hull, an ingenious design feature that American automotive engineers had adapted from civilian truck maintenance practices. The Jagdpanzer IV's engine replacement required specialized lifting equipment, extensive disassembly of surrounding components, and minimum 8 hours even under ideal workshop conditions. Field repairs demanded improvisation and considerable technical expertise that only experienced mechanics possessed. This difference translated to operational availability statistics that favored American design despite its less sophisticated engineering. Hellcats could return to combat after mechanical failures within hours. German tank destroyers required days. The crew ergonomics evaluation produced unexpected insights into how design philosophy influenced combat effectiveness. The Hellcat's open-topped turret that seemed like obvious vulnerability actually provided exceptional situational awareness. Crew members could observe battlefield conditions without relying solely on vision ports and periscopes that limited fields of view. This awareness enabled faster target acquisition and better tactical decision-making, advantages that partially compensated for the exposure to artillery fragments and small arms fire. The Jagdpanzer's enclosed fighting compartment provided protection, but imposed significant penalties in crew efficiency. Limited visibility forced commanders to rely on brief periscope observations that couldn't match the comprehensive battlefield awareness American crews enjoyed. The casemate design's restricted traverse arc meant drivers had to reposition the entire vehicle to engage targets outside the narrow firing sector, a maneuver that consumed time and exposed the tank destroyer to return fire during the alignment process. Steiner's interim report, filed in December 1944, contained observations that would have seemed heretical to the German engineering establishment 18 months earlier. The American Hellcat represents a fundamentally different approach to tank destroyer design, prioritizing tactical mobility and simplified logistics over protection and mechanical sophistication. While inferior to German designs in armor protection and precision engineering, the vehicle achieves superior operational effectiveness through characteristics that current Waffenamt specifications do not adequately value. The engine's automotive-grade construction enables rapid field maintenance that keeps vehicles operational under conditions that would sideline more complex German designs. The simplified transmission requires minimal operator training while providing reliable performance that sophisticated German systems achieve only through extensive crew expertise and careful maintenance. Most significantly, the power-to-weight ratio enables tactical maneuvers that render armor protection less critical through avoiding enemy fire rather than absorbing it. These conclusions challenged core assumptions about what constituted effective armored vehicle design. German doctrine had always emphasized engineering excellence, measured through precision manufacturing, sophisticated mechanical systems, and balanced performance across all capability dimensions. The Hellcat succeeded by rejecting this balanced approach, accepting severe limitations in protection to achieve mobility that changed fundamental tactical calculations about how tank destroyers should be employed. The speed demonstrations that Steiner conducted for visiting Wehrmacht officers produced reactions that revealed how deeply the Hellcat challenged German military thinking. During one memorable trial in late December, the American vehicle accelerated from standing start to maximum speed on the Kummersdorf test track, maintaining 55 miles per hour through straightaway before braking to complete stop in distance that German observers found impossible to believe without witnessing personally. General Major Kurt Hoffmann, attending as representative from Oberkommando des Heeres, watched the demonstration with expression that shifted from skepticism to stunned recognition. "How fast did you say?" he demanded, as if hearing the number again might reveal a calculation error that explained the impossible performance. 89 kilometers per hour, on level road surface, Steiner confirmed, consulting his stopwatch. Consistent across multiple trials, the vehicle achieves this speed reliably without mechanical stress that would indicate operating beyond design limitations. Hoffmann walked slowly around the Hellcat, studying the thin armor plates and exposed turret mechanism with visible confusion. "This is faster than our reconnaissance vehicles, faster than the Puma armored car by a significant margin. How is this possible in a 17-ton tracked vehicle mounting a 76mm gun?" Steiner had prepared a comprehensive technical explanation, but he recognized that Hoffmann's question demanded a different answer. The Americans asked different questions than we did when designing tank destroyers. We asked how to build a vehicle that could survive frontal engagement with enemy armor. They asked how to build a vehicle that would never need to engage frontally because it could always choose advantageous firing positions through superior mobility. The distinction seemed subtle, but it represented a fundamental philosophical difference that separated German and American approaches to armored warfare. German engineering pursued optimal solutions across all performance dimensions, accepting complexity and production difficulty to achieve vehicles that dominated when employed according to doctrine. American design focused on specific tactical requirements, sacrificing everything that didn't directly contribute to that mission profile. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The testing continued through winter 1944 and into early 1945, as Steiner's team accumulated data that consistently contradicted comfortable assumptions about technical superiority. The Hellcat completed 237 kilometers between mechanical failures, requiring more than routine maintenance. The Jagdpanzer IV averaged 112 kilometers between similar breakdowns, a difference attributable to the American vehicle's simplified design that reduced component count and potential failure points. Turret traverse speed comparisons revealed another unexpected advantage. The Hellcat's manual traverse mechanism, seemingly primitive compared to German-powered systems, actually enabled faster target tracking because it responded instantly to gunner input without hydraulic lag. German crews appreciated their powered traverse for reducing physical fatigue during extended operations, but they acknowledged the American manual system provided better responsiveness during rapid engagement sequences. The ammunition stowage analysis demonstrated how American designers had optimized for sustained combat operations. The Hellcat carried 45 76mm rounds in racks positioned for rapid loader access. The Jagdpanzer IV carried 48 75mm rounds, but their positioning required awkward crew movements that slowed reload cycles. American crews could sustain higher rates of fire because their designers had considered ergonomics alongside technical specifications. Perhaps most revealing were the maintenance trials that Steiner conducted using average German mechanics rather than specialized technicians. The Hellcat's automotive-grade components could be serviced using standard workshop tools and procedures familiar to anyone with civilian vehicle experience. The Jagdpanzer IV demanded specialized knowledge of Maybach engine systems, German transmission architecture, and complex suspension geometries that only military-trained mechanics fully understood. This difference had profound implications for operational logistics. American units could maintain their Hellcats using personnel with minimal specialized training, drawing on the vast pool of civilian mechanics that Detroit's automotive industry had trained over decades. German forces required experienced military technicians who understood sophisticated systems that no civilian equivalent prepared them for, limiting the available personnel pool and making battlefield repairs more dependent on scarce expertise. The captured ammunition that Steiner's team acquired revealed another dimension of American pragmatism. The standard M62 armor-piercing round achieved modest penetration performance, sufficient for defeating most German tank side armor, but inadequate against Panther or Tiger frontal plates. But American designers hadn't attempted creating a single round that could defeat all targets under all conditions. Instead, they'd developed specialized ammunition for specific tactical situations. The T4 HVAP round, using a tungsten carbide penetrator, could defeat even Panther frontal armor at moderate ranges. Production limitations meant these rounds remained scarce, but American doctrine accepted this constraint by training crews to use standard ammunition against vulnerable angles and reserve HVAP rounds for situations requiring frontal penetration. This flexible approach contrasted with German tendency toward developing universal solutions that worked optimally in all circumstances but often arrived too late or in insufficient quantities. Steiner's team also evaluated the Hellcat's high explosive capabilities, discovering another compromise that American designers had accepted. The 76mm HE round carried less explosive content than German equivalents, limiting effectiveness against infantry and fortified positions. But American doctrine didn't expect tank destroyers to serve as general-purpose combat vehicles. They were designed for engaging armor, with other units providing capabilities that Hellcats lacked. German designs attempted more balanced capability sets, producing vehicles that could handle multiple mission types but excelled at none. The reliability data that accumulated over months of testing told a story that Steiner found increasingly difficult to reconcile with his engineering training. The Hellcat shouldn't have been so dependable. Its commercial-grade components, simplified systems, and lightweight construction suggested vehicles that would require constant maintenance and frequent major repairs. Yet testing revealed the opposite. The American design proved more reliable than German vehicles engineered to higher standards, using superior materials through more sophisticated manufacturing processes. The explanation, Steiner gradually realized, lay in understanding reliability as systems-level property rather than component-level characteristic. German designs achieved individual component excellence through precision manufacturing that minimized tolerances and optimized performance. But complex systems with many precision components created opportunities for failures that simpler designs avoided. The Hellcat's crude components worked together reliably because the overall system had fewer potential failure modes, accepting individual component limitations to achieve better system-level performance. This insight challenged fundamental assumptions about engineering methodology. German education emphasized pursuing optimal solutions through rigorous analysis and precise execution. The American approach seemed almost careless by comparison, accepting adequate component performance to achieve system-level objectives. Yet battlefield results consistently favored American methodology, suggesting that optimal components didn't necessarily produce optimal systems when complexity and logistics constraints were factored into effectiveness calculations. The direct comparison with German tank speed capabilities highlighted the Hellcat's revolutionary performance. Panther tanks achieved 46 km/h maximum road speed, impressive for a 45-ton vehicle, but modest compared to American design. Tiger tanks topped out at 38 km/h, though cross-country performance rarely exceeded 20. Even the Panzer IV, Germany's most numerous tank throughout the war, managed only 42 km/h under ideal conditions. The Hellcat's 89 km/h represented performance that exceeded every German armoured vehicle by margins that seemed impossible without understanding the radical design philosophy that enabled it. American engineers had inverted traditional priorities, treating speed as primary characteristic and accepting whatever limitations that emphasis imposed on other capabilities. German designers would never have approved such an unbalanced approach, yet the battlefield results from Aracourt and similar engagements demonstrated its effectiveness. Steiner's testing included capturing performance data during simulated tactical scenarios that replicated actual combat conditions. The Hellcat could accelerate from concealed position, engage targets at 300 meters, and return to cover within 18 seconds. German tank destroyers required 40-plus seconds for equivalent maneuver, a difference that meant American crews could execute multiple engagement cycles before German units completed single tactical repositioning. The implications extended beyond individual vehicle performance to operational-level calculations about force employment. A battalion of Hellcats could cover more terrain, respond to more tactical situations, and sustain higher operational tempo than equivalent German formations, despite having less armor protection and comparable firepower. Speed enabled tactical advantages that protection couldn't match, challenging German doctrinal emphasis on survivability through armor as fundamental design priority. The crew interviews that Steiner conducted with German tankers who had faced Hellcats in combat provided context that technical testing couldn't capture. Oberfeldwebel Hans Richter, Panther commander who had survived the Aracourt engagement, described the psychological impact of fighting vehicles that refused to accept conventional armor battle conditions. They would appear from nowhere, Richter explained, still visibly affected by memories of that September morning. We would traverse to engage, but before our gun could bear, they had already fired and relocated. You couldn't predict where they would appear next because they moved faster than seemed possible for a tracked vehicle. Our training emphasized frontal engagement where our armor advantage would dominate. These American machines never gave us frontal engagements. They chose angles and timing that defeated our advantages. Another veteran, Lieutenant Peter Schmidt, described attempting to pursue withdrawing Hellcats after unsuccessful engagement. We advanced at maximum speed, trying to close range before they could escape. But the maximum speed for Panther is 46 km/h. The Americans were doing 70-80 kilometers. We couldn't catch them. We couldn't force them to fight on our terms. This violated everything we understood about armored tactics, where heavier vehicles should dominate through superior firepower and protection. These testimonies revealed psychological dimensions that Steiner's technical analysis couldn't quantify. German crews had trained on doctrine that emphasized their vehicles' technical superiority over Allied equipment, encountering enemies that refused to fight according to rules that favored German advantages created uncertainty that affected tactical decision-making. The knowledge that American tank destroyers could appear anywhere, engage from unexpected angles, and escape before German response could organize, forced German commanders to adopt defensive caution and surrender initiative. Steiner's final comprehensive report, completed in March 1945 as the Reich's territorial control collapsed, contained analysis that represented a professional epitaph for German engineering philosophy's application to armored warfare. The document totaled 87 pages of detailed technical assessment, performance data, and tactical evaluation that collectively challenged every comfortable assumption about what constituted superior combat vehicle design. The executive summary opened with an observation that would have been considered defeatist heresy earlier in the war. The American M18 Hellcat achieves superior operational effectiveness compared to German tank destroyer designs, despite demonstrable inferiority in armor protection, mechanical sophistication, and precision manufacturing. This paradox demands reconsideration of fundamental assumptions underlying Waffenamt vehicle development doctrine. Steiner documented the specific areas where German designs maintained clear advantages: armor protection that provided genuine survivability against most Allied weapons, main gun performance that exceeded American equivalents in penetration and accuracy, sophisticated fire control systems that enabled first-round hit probability German crews could rely upon, manufacturing quality that reflected decades of precision metalworking tradition. These advantages remained real, measurable, and significant under the tactical conditions German doctrine anticipated. But the Hellcat succeeded by making those advantages irrelevant through refusing to create tactical conditions where they mattered. The American vehicle couldn't survive hits from German guns, so it avoided being hit through mobility that prevented German gunners from acquiring proper aim points. It couldn't penetrate Panther frontal armor at long range, so it closed to flank angles where 80mm side plates became vulnerable. It lacked the mechanical sophistication of German designs, so it employed components reliable enough that sophistication became unnecessary complexity. The production cost analysis provided damning evidence about resource efficiency. German accounting indicated Jagdpanzer IV production costs exceeded 58,000 Reichsmarks per vehicle, excluding weapons and communications equipment. American procurement documents that German intelligence had captured suggested Hellcat manufacturing costs approximated $55,000, roughly equivalent to 46,000 Reichsmarks at official exchange rates. Similar costs, but the American vehicle could be produced faster, using less specialized labor and more readily available materials. More significantly, maintenance costs favored American design by substantial margins. German tank destroyers required specialized replacement parts manufactured to tight tolerances using specific alloy compositions. Supply chain disruptions or manufacturing bottlenecks could sideline operational vehicles awaiting components that couldn't be improvised or substituted. Hellcat repairs often utilized commercial automotive parts that American logistics networks supplied in overwhelming abundance, enabling field maintenance that kept vehicles operational under conditions that would have immobilized German equivalents. The training requirements comparison revealed another dimension of American design efficiency. German tank destroyer crews required extensive instruction in operating sophisticated mechanical systems, understanding complex fire control procedures, and maintaining vehicles whose engineering demanded specialized knowledge. Training programs consumed months and required experienced instructors who understood systems that no civilian equivalent prepared students for. American crews achieved combat effectiveness after 8 weeks of training that emphasized tactical employment over mechanical sophistication. The Hellcat's automotive-grade systems operated according to principles familiar to anyone with civilian vehicle experience. The simplified fire control required understanding basic gunnery fundamentals rather than mastering complex German methodologies. This training efficiency meant American replacement crews could achieve acceptable combat effectiveness quickly, while German crews needed extensive preparation before deploying to combat units. Steiner's analysis of combat effectiveness ratios provided the most uncomfortable evidence about American design success. The Hellcat achieved 2.4-to-1 kill-to-loss ratio across all theaters, meaning American crews destroyed nearly 2.5 German armored vehicles for every Hellcat lost. This performance exceeded German tank destroyers' ratios despite the American vehicle's obvious design limitations. The explanation lay in understanding that tactical effectiveness measured total system performance rather than individual component excellence. The document concluded with recommendations that acknowledged realities German high command no longer had capacity to address. Future armored vehicle development must prioritize operational availability and tactical mobility, alongside traditional emphasis on protection and firepower. The American Hellcat demonstrates that adequate performance across limited mission parameters can exceed excellent performance across a broader capability spectrum when logistical constraints and tactical employment are properly considered. German engineering excellence has produced vehicles that dominate when deployed according to doctrine, but American pragmatism has created vehicles that function effectively under actual battlefield conditions. These recommendations arrived too late to influence German war production. By March 1945, the Reich's industrial capacity had collapsed, under combined effects of strategic bombing, territorial losses, and resource exhaustion. The engineering insights Steiner documented would inform post-war analysis, but couldn't affect wartime outcomes. The Hellcat had already proven its effectiveness through thousands of combat engagements across European and Pacific theaters. The personal cost of Steiner's intellectual honesty became apparent in April 1945 as Soviet forces approached Kummersdorf. His comprehensive report documenting American technical advantages could be interpreted as defeatism or insufficient commitment to German victory. Several colleagues advised him to destroy potentially compromising documents before evacuation, but Steiner recognized the report's value extended beyond immediate military circumstances. Future engineers would need to understand why German technical excellence had proven insufficient against Allied industrial pragmatism. He arranged for the report's secure storage, with several trusted colleagues who would survive the Reich's collapse, ensuring the analysis would be available to post-war researchers. The captured Hellcat itself was destroyed during the final defensive battles around Berlin, but Steiner's technical documentation preserved a detailed record of what German engineers had learned from testing the revolutionary American design. The broader implications of the Hellcat's success extended beyond tank destroyer tactics to fundamental questions about engineering philosophy in total war conditions. German industrial culture emphasized craftsmanship, precision, and technical excellence as expressions of national character. These values produced remarkable achievements: V-2 rockets, jet aircraft, advanced U-boats, heavy tanks that dominated when conditions favored their employment. But the same values created vulnerabilities that Allied industrial capacity exploited ruthlessly. American engineering accepted adequate performance that could be mass-produced, rather than pursuing optimal performance that required specialized manufacturing. This philosophy enabled production volumes that overwhelmed German technical advantages through numerical superiority. Detroit's automotive industry produced tanks, aircraft, and vehicles using methodologies refined through decades of civilian mass production. German aircraft and vehicle manufacturers adapted precision metalworking traditions that prioritized individual excellence over production efficiency. The Hellcat exemplified this American approach. Its automotive-grade components came from supply chains geared for producing millions of civilian vehicles annually. Its simplified systems could be manufactured using general industrial capacity rather than requiring specialized military production facilities. Its design accepted limitations that German engineers would have considered unacceptable, but those limitations enabled production at scale that made individual vehicle performance less critical than aggregate fleet capabilities. The production numbers told compelling stories about competing industrial philosophies. Buick manufactured 2,507 Hellcats between July 1943 and October 1944, 15-month production run that supplied American tank destroyer battalions with purpose-built vehicles optimized for their specific mission requirements. German industry produced approximately 2,000 Jagdpanzer IV tank destroyers across similar time frames, comparable output that suggested rough production parity, but American industrial capacity simultaneously produced thousands of Sherman tanks, M10 Wolverine tank destroyers, M36 Jackson tank destroyers, and vast quantities of supporting equipment that German production couldn't match. The Hellcat represented one element of an integrated industrial system that treated military production as an extension of civilian manufacturing rather than a specialized endeavor, requiring unique capabilities. German production attempted sustaining multiple competing designs using limited specialized capacity, creating bottlenecks that left units under-equipped despite individual vehicle excellence. The strategic implications became clear during the Ardennes offensive in December 1944, when German forces attempted a massive counterattack that temporarily caught Allied forces unprepared. Initial German successes demonstrated that tactical excellence and surprise could still achieve local victories despite overall material disadvantage. But American industrial capacity enabled rapid response that German logistics couldn't match. Hellcats from multiple battalions converged on threatened sectors within days, their mobility enabling strategic redeployment that German tank formations couldn't accomplish. The 705th Tank Destroyer Battalion's defense of Nouville on December 19th and 20th demonstrated how Hellcat speed enabled aggressive tactics that disrupted German timetables. Just 4 Hellcats, supporting airborne infantry, engaged elements of 2nd Panzer Division in a spoiling attack that destroyed at least 30 German tanks and inflicted between 500 and 1,000 casualties on attacking forces. The Hellcat crew's ability to shoot and scoot at speeds German tanks couldn't match created tactical confusion that amplified their numerical impact. German commanders couldn't predict where American tank destroyers would appear next because their mobility enabled repositioning faster than German doctrine anticipated. Panthers and Tigers designed for frontal slugging matches found themselves engaged from multiple angles by opponents who refused to fight according to rules that favored German advantages. The post-war analysis of Hellcat effectiveness revealed patterns that Steiner's testing had predicted. Units that employed the vehicle according to tank destroyer doctrine achieved exceptional results. Battalions that attempted using Hellcats as general-purpose combat vehicles suffered higher casualties and reduced effectiveness. The design's specialized optimization meant it excelled in its intended role, but struggled when misemployed in missions requiring capabilities American designers had deliberately sacrificed. The 704th Tank Destroyer Battalion, which had conducted initial testing and refined tactical employment doctrine, destroyed over 90 German armored vehicles during European operations while suffering modest losses. Their success stemmed from understanding the Hellcat's capabilities and limitations, employing it in ambush and rapid maneuver roles that exploited speed while avoiding sustained engagements where thin armor would prove fatal. Other battalions learned similar lessons through costly experience. Early attempts to use Hellcats for infantry support or static defensive positions resulted in unnecessary casualties when thin armor failed to protect crews from artillery fragments or small arms fire. The open-topped turret that provided excellent situational awareness during mobile operations became a liability in urban fighting or fortified positions where overhead protection mattered more than visibility. The learning curve demonstrated the importance of matching tactical doctrine to vehicle capabilities, a lesson that applied equally to German forces struggling to adapt vehicles designed for different warfare conditions. Late-war German tank destroyers like the Jagdpanther represented evolutionary refinement of traditional design philosophy. Excellent armor, powerful gun, sophisticated engineering, but they arrived too late and in insufficient numbers to affect strategic outcomes already determined by industrial capacity disparities. The Hellcat's legacy extended beyond its immediate wartime impact to influence post-war armored vehicle development across multiple nations. The design demonstrated that specialized vehicles optimized for specific missions could outperform more balanced general-purpose designs when employed according to appropriate doctrine. This lesson informed American thinking about future combat vehicle requirements, leading to continued emphasis on mobility and firepower over protection in subsequent tank destroyer and reconnaissance vehicle programs. The M41 Walker Bulldog light tank, developed in the war's immediate aftermath, incorporated many lessons from Hellcat experience. High power-to-weight ratio, enabling superior mobility. Simplified systems facilitating field maintenance. Automotive-grade components provide reliability without requiring sophisticated engineering. The design philosophy that American engineers had refined through wartime experience continued shaping post-war vehicle development. Soviet designers studying captured American equipment reached similar conclusions about mobility's tactical value. Post-war Soviet armored vehicle development increasingly emphasized speed and agility alongside traditional Soviet priorities of simple construction and mass production capability. The T-54 medium tank, which became the most numerous tank design in history, reflected understanding that adequate performance produced reliably trumped excellent performance achieved inconsistently. Even German engineers rebuilding their nation's defense industry under Allied occupation absorbed lessons from Hellcat analysis. The Bundeswehr's early armored vehicles emphasized reliability and maintainability over the sophisticated engineering that had characterized Wehrmacht equipment. The recognition that operational availability mattered more than theoretical performance specifications represented a fundamental shift in design philosophy that Steiner's wartime analysis had documented. The final irony of the Hellcat story emerged from recognition that German tankers had been right about one thing. By conventional metrics of armored vehicle design, the American tank destroyer was inferior. Its thin armor provided minimal protection. Its commercial-grade components lacked sophistication. Its simplified systems sacrificed capabilities that German designs provided. Every technical criticism German crews had leveled against American equipment was factually accurate, but those criticisms missed the fundamental point that American designers had understood. Effectiveness measured achievement of mission objectives, rather than excellence across arbitrary performance dimensions. The Hellcat couldn't survive frontal engagement with Panthers, so it avoided frontal engagements. It couldn't match German mechanical sophistication, so it achieved reliability through simplicity rather than precision. It couldn't compete in areas where German advantages dominated, so it competed in areas where American advantages proved decisive. This understanding represented a cognitive shift that German engineering culture struggled to accept even as battlefield evidence accumulated. The belief that technical excellence inevitably produced superior battlefield performance was too deeply embedded in German military tradition to abandon easily. Yet the evidence became undeniable. American pragmatism had defeated German perfectionism through understanding that adequate solutions produced abundantly, outperformed optimal solutions produced scarcely. The morning fog outside Aracourt had concealed more than just tactical positions. It had hidden a fundamental truth about industrial warfare that neither side fully understood when the battle began. Speed and availability trumped protection and sophistication when tactical doctrine exploited mobility advantages while accepting vulnerability constraints. Werner von Seegroth's Panthers represented the pinnacle of German engineering achievement, but Edwin Leiper's Hellcats represented a more effective answer to the tactical question modern armored warfare actually asked. The German tankers who tested the captured M18 Hellcat had admitted they'd never seen 55 miles per hour in a tank because no German designer had ever considered that speed more important than armor or sophisticated mechanical systems. That admission represented more than simple technical observation. It acknowledged fundamental differences in design philosophy that German and American engineers had pursued throughout the war. The difference between pursuing perfection across balanced capabilities versus accepting radical compromises to maximize specific performance characteristics. The Americans had built vehicles that violated every principle German doctrine considered essential, yet succeeded through making those principles irrelevant to tactical situations it created. The Hellcat couldn't fight German tanks on German terms, so it forced German tanks to fight on American terms where speed, mobility, and tactical flexibility defeated armor and firepower. This inversion of conventional wisdom represented intellectual achievement as significant as any technical innovation the vehicle incorporated. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.